Alright, so URI Physics 203 with Amir Hadzik, 2015. This is the infamous rocket problem. A few people asked me to do it on camera, so we're going to see how I do, try my best. So here we go. We initially have a rocket, and we're going to make our little diagrams over here. So initially, there's a rocket. We'll make ourselves a beautiful rocket. And it's traveling at a speed v and at a weight or mass of m. Very simply, that's all it's doing, moving through space. Now we have a second rocket. This rocket is the exact same as the first. Pardon me on my pictures, they are helpful. Except here, it's moving a little bit faster and with a little bit less mass. So we're going to equate that with v plus dv, velocity plus the change in that velocity to make it faster, and then m plus dm. Now, even though it's lost mass, dm's negative, so it really doesn't matter as things go along. So this right here is going to be traveling a v final. We're just going to label it as such. V final, assume v when I write it as v initial. Now there are also particles down here. They're being expelled this direction, the opposite direction of the actual velocity, and that's going to be your exhaust. And remember, in class we used the variable, this guy, that's the velocity of the exhaust. We're going to use that for this problem. So to equate this, bring it into terms, we're going to use law of conservation of momentum. So simply, P initial is equal to P final. Now what that really means is the exact same thing as you think it means. It's just this problem makes it a lot more complicated. So very simply enough, we look at this and it's traveling a velocity at a mass. So what is momentum in this scenario? Well, it's simply P initial is equal to mv. Now over here, it's a little different. Yeah, if you think it's changing, but changing continuously as the problem goes along. So we have to relate a few things using these up here. So P final is equal to m plus dm times, this is, v plus dv plus, no, don't do that, minus, well, you add the negative dm, because dm is negative, dm, and then v final, right? Now don't ask me how to explain this per se, know how to do this. Think of this as mv, and you're just equating the two, and then you're subtracting the momentum that was lost from the particles leaving the system. So next we're going to clean this up a little bit on this side, and we're going to FOIL it out. So momentum final is also equal to mv plus mdv minus velocity final minus, we're going to kind of velocity initial divided by the velocity of the exhaust, and then all of that times dm, if I'm not mistaken. Alright, so this is starting to look a little bit more like your momentum problem that you're used to looking at. So over here, we're going to do some backpedaling for a second. We're going to talk about what momentum and how we're going to relate this to getting our final answer. And to do that, we need to talk about force for a second. Force, right here, is always equal to the change in momentum over the change in time. So dp over dt, right? And with that being said, we have up here that momentum final and momentum initial. So what we can do is we can simply say that dp is equal to pf minus pi. Right. So let's do the math. I'm not going to explain it, but you do some simple subtraction, and you get that dP is also equal to mdv minus velocity of the exhaust dm. Okay, there we go. So, with that being said, we can also say something else about force. What is force always equal to? ma. In this situation, the acceleration is g. So force is also equal to mg. Right? No argument there. So we're going to come down here, and we're going to set this right here, and we're going to take it and we're going to divide it all by dt, so we can create dp dt, so we can equate it to mg. So next we're going to say dp over dt is equal to mdv over dt minus velocity of the exhaust dm over dt. Which is, oh wait, 1 second. We can also quickly point out that the m's will cancel, you know what, no, okay, because we're going to equate this now to mg. M's will cancel here, and we're going to divide this by m. So we're going to say now that g is equal to, and here we go, yep, it is dv over dt plus v over m. Yeah, dm dt. All right. So a little bit of algebra, but this is where your algebra ends. Also, g is negative since it's pointing down. Little things. Now your calculus begins. Since this is obviously calculus-based course, we gotta throw that in there somewhere. So we're gonna do a couple of simple integrations. Negative sign comes out front. Integral from t0 to t, whatever t they so choose, of g dt. Right, because we also multiplied. So yeah, just say dt right there, just g dt, right? Anyway, continuing on is equal to the integral from v initial to v final of dv plus the integral of the velocity of the exhaust divided by m dm. And that's from m initial to m final to equate for the loss of change in m. And really, after showing this step right here, that's proof enough to be able to come to the conclusion that, well, this becomes v, you know what, here, wait, we're just going to do this all at the same time. So this is negative gt, right, because dt becomes t, g is constant, so it stays, right, is equal to just simply v, right, plus, and this is velocity of the actual the exhaust, and then ln of mass initial over mass final. Now this isn't the actual formula that you usually see it in, and simplified further, it becomes v is equal to v initial plus the velocity of the exhaust ln of mass initial divided by mass final, and then subtract gt, and that is your answer. Hope that helps, and see you in a bit for the other problem.